So it's really a great honor for me to be here in this very special occasion. So I know Spenta, having known Spenta for 10 years, and we first met at CERN, I think, when I was a junior staff there, and we became very quickly good friends, and we had a lot of personal affinity. And I think part of this personal affinity is based on two things. The first thing is that I think we mostly agree on what is garbage and what is not. And the second thing is that we are both inspired by Marxist philosophy. So,
oh my God!
you see, he's like your uncle to me. Okay, so I'm going to talk today about a topic which I think is.
Start by singing the international.
Yes. No, we will end by singing the international. But in Russian, So I'm going to talk today about the non-interacting fermions, strings, and the one-over-n expansion. And I think this is a good topic for this conference because I think one of the leitmotifs in the work of Spenta has been the interplay between non-interacting fermions, strings, and the one-over-n expansion. If you look at his papers, you see this interplay constantly appearing in many different ways. For example, his paper on unitary matrix quantum mechanics exploited this fact a lot. I mean, the appearance of a system of n fermions living in this Mathieu potential, and this was the key to solving this problem. Then also, of course, in his work on the C=1 strings and on the bosonization of non-relativistic fermions and so on. So in this talk, I will present another example of this interplay. And this interplay generally involves a system of n non-interacting fermions, which in the 1/n expansion turns out to be equivalent to string theory. Now, one of the reasons why I'm interested in this kind of interplay is that the mathematics involved in these two sides are very different. Now, this side typically involves quantum mechanics, operators, spectrum, and this other side usually involves, in the examples I want to consider, enumerative geometry, combinatories, and so on. And one of the reasons why these large n dualities are so powerful is because they lead you to equivalences between very different mathematical objects. So different that very few mathematicians know both sides simultaneously. Okay, and this I can tell you is one of the problems that we face when we talk to mathematicians. Now, what I'm going to tell you today is not an isolated example. It's really very similar to things that have happened in the past. It's very similar to C=1 strings and C<1 strings. And it's also similar to the Jamil's theories, which also involve this interplay between systems of fermions and the enumerative geometry of covariance of Riemann surface. So let me explain you a little bit more. What is the object I'm going to consider? So the string theory that I'm going to consider here are topological strings on non-compact Calabi-Yau manifolds. And these were explained a little bit by Narayan in his talk yesterday. So the difference is that I'm going to focus mostly on non-compact Calabi-Yau manifolds because these are actually solvable models in the genus expansion of string theory. And they have many applications. This is not just a completely academic example. One of the applications they have is that they engineer n=2 supersymmetric gauge theories. You can actually realize supersymmetric gauge theories and compute holomorphic quantities in supersymmetric gauge theories by using topological strings. The second reason why these theories are important is because they have a connection to a very rich branch of mathematics, which is enumerative geometry. And what has been discovered in the last 20 years is that topological strings are the physical counterpart to the mathematical counting of holomorphic maps in Calabi-Yau manifolds. Now, the basic quantity that you want to calculate in topological string theory, in closed topological string theory, is this genus G free energy that Narayan was explaining how to compute in a Wall-Street definition. And I'm not going to give you more details, but what I want to insist is that in the case of non-compact Calabi-Yau manifolds, the problem of calculating this genus by genus is completely solvable, thanks to a lot of work that has been done in the last 20 years. So it can be computed recursively. There are various methods to do that. One is based on the holomorphic anomaly equations of Versace, Cecotti, Guri, and Baff. Another method was developed by ourselves by our group 10 years ago. And these are actually very powerful methods that actually make it possible to calculate these functions to 100 loops in one week of running a program in the computer. And these are actually functions, complicated functions of the Calabi-Yau modeling. So the fact you can compute this to genus 100 is actually non-trivial. And it turns out that these functions are very rich because they encode all this information of holomorphic mappings from one Riemann surface to the Calabi-Yau. And in particular, they can be expanded in terms of wall-seat instanton contributions and the coefficients that appear when you expand these functions in powers of e to the minus lambda. Here, lambda is the modulus of the Calabi-Yau. Here, for simplicity, I'm assuming that I have one single modulus, but this is just for expository purposes. Of course, you can consider more general cases. Now, I was saying that the coefficients that appear here are these famous Gromov-Witten invariants, which are very important enumerative objects in modern algebraic geometry. Okay, so what's the problem with a genus-by-genus approach? Well, the problem of a genus-by-genus approach is that the string perturbation theory in these theories diverges. And this is something that has been known to be the case for general string theories. So if you fix the moduli and you consider these functions at a fixed value of lambda for large values of g, they diverge doubly factorially, okay, when g is large. Now this means that if you consider the standard quantity, the all genus perturbative series, this is going to be given by a series of this type where gs is the string coupling constant, and this series is just asymptotic. It's a formal series because the coefficients diverge like 2g factorial. This is a universal problem in any string perturbation theory. Now, the question you can ask when you are faced with a problem like this is the following. Is there a well-defined function such that this asymptotic series is its asymptotic expansion at a small string coupling? So is there a non-perturbative completion of this series? And this is the kind of question that we have to solve in general string theory if we want to go beyond the string perturbation series. And what I'm going to try to do in this talk is to propose you an answer for these particular models. These are not very physical models, but they are interesting models in which we actually can solve this question. Of course, this question can be also solved using ADS-CFT theory, where the non-perturbative completion is given by the corresponding quantity computed in a gauge theory. Okay, so in order to answer this question, to give you what is the quantity which is behind this asymptotic series, I have to be a little bit more explicit about the Calabi-Yau geometry. Now, it turns out that non-compact Calabi-Yaus are very special. Calabi-Yau manifolds that you consider in string theory are usually 6-dimensional. But it turns out that in the non-compact case, the non-trivial geometry of the Calabi-Yau is encoded in an algebraic curve, in an equation of the form W of Ex to Ep equal to 0. Now, once you are given this function here, which describes an algebraic curve, the Calabi-Yau threefold is defined by an equation like this, where U, V, Ex, and Ep are complex variables. So you see this is one equation for 4 complex variables, so it defines a 3-dimensional manifold. But the non-trivial geometry is encoded in this function here. Now, these functions I've just given you here 2 examples. Out of this type, they are like polynomials in e to the x, e to the minus x, e to the p, and e to the minus p, and they involve a quantity kappa, which is the modulus of the Calabi-Yau manifold. Now, I'm using 2 notations for the modulus, kappa and lambda, and this is because, for those of you who are experts, you know, when you parameterize the modulus of Calabi-Yau manifolds, you can do different choices. One is the choice that appears in the equation, and the other is the choice that defines what is called a flat coordinate of moduli space. And this difference is important because, as we will see, we'll have to identify this with a sort of gauge theory quantity, and for this we need the appropriate coordinates. So choice of coordinates is important, but here this is a modulus just like lambda is. And lambda and kappa are related by some non-trivial equation. Okay? Yeah, the reason is that because, you know, when you want to calculate things on these manifolds, you want to introduce a differential form. And it turns out that the differential form in these manifolds is actually x times p times dx. So if you wanted to write this as a variable capital X, say, you would have to introduce logs. Okay, so either you introduce logs in the differential forms on this curve, or you introduce exponentials. But there is really an issue of exponentiation here, which is... Sorry? Exactly. So they have to be defined on this exponentiated curve. This is going to be crucial later on, as you will see. Okay, so how do you go from this system to Fermions? Well, the main idea is to think about these curves as Fermi droplets in some phase space xp. So let's take, for example, this equation that I was writing before, and imagine that you consider the equation defined by this polynomial equal to e to the e, where e is going to be interpreted as an energy. I want to interpret now this curve, the interior of this curve, as a Fermi droplet of fermions which have a Fermi energy given by E. Similarly, you can do this game for all these equations. For example, here you have this other equation, Ex plus Ep plus e to the minus x minus p equal to Ee, and you see that this defines a Fermi droplet with Fermi energy E, and you see that the geometry of the curve gives you different geometries for this Fermi surface. So you have different Fermi surface for these systems. And of course, this is just a classical picture because just drawing the Fermi droplet is just giving you the semi-classical description of the putative Fermi gas which is behind this. But if you want to go to a quantum theory, you should if you want to interpret this as a sort of Fermi gas, you should actually quantize this curve. You should quantize these variables xp, because if you want to interpret x and p as coordinates, as canonical variables of some classical system, quantization is just promoting x and p to Heisenberg operators. And this is very interesting, because this means that we want to actually quantize the target geometry where this string theory lives. And you will see that this actually gives you access to the string perturbation series. So, technically, it's very simple. We just take x and p in these functions, and we promote it to canonically conjugate Heisenberg operators, which commute to I h bar. H bar is real and positive. And it turns out that when you do quantization of the monomials appearing in this curve, you have to be careful with ordering ambiguities, but you can fix them by using bulk quantization, which is very appropriate to exponentiated operators. And it turns out that when you do that, any curve will produce for you a self-adjoint operator on L2R. So, for example, in the example that I was writing you before, you have e to the x plus e to the minus x plus e to the p plus e to the minus p. Now you just promote this to an operator, and you get this operator that you can introduce in an exercise sheet in Quantum Mechanics 1, or you can introduce all these other operators. Now the question is, what is the nature of these operators? What kind of a spectrum they have as quantum mechanical operators? We are not used to work with exponential operators in quantum mechanics, so what is the kind of a spectrum you will have? Now it turns out that these operators are as good as they can get. Now it turns out that what you have to do is to look to the inverse operator to these guys, and these operators turn out to be of trace class. This was something that we conjectured with my student and my postdoc, and it was later proved by myself and Rinat Kashaf, and it was also proved by Leon Taktayan, who is here. I didn't expect to have Leon in ICTS, but this is the good thing of a great institute. You meet people that you didn't even know that were coming, and you can discuss with them and so on. So these operators are of trace class. So what this means is this trace class? Well, this trace class is actually a very interesting property. If an operator is trace class, first of all, it's going to be compact, it's going to have a discrete spectrum. So the spectrum of this operator, I'm going to write it as e to the minus en. N is 0, 1, and so on. And being of trace class means, in addition, that all the traces of positive powers of these operators are bounded and by infinity. And these are, in a sense, the best kind of operators that you can have in quantum mechanics. And these are the operators that, in mathematical books of quantum mechanics, they tell you that they can represent density matrix of quantum mechanical systems. And you see, the fact that you have a discrete spectrum means that this is very similar to confining potentials in Schrödinger theory. And actually, it's very easy to see that if you take this, for example, this operator that I was writing you before, you take h bar equal to 2 pi, you can compute numerically its spectrum as its wave functions, and you get the kind of thing that you would find by diagonalizing a confining potential in Schrödinger theory. You would get a ground state with no nodes, a first state state with one node, second state state with 2 nodes, and so on. So these operators are very concrete. You can study numerically, you can study the spectrum, and so on. Now, my claim will be that the details of this spectrum actually contain information about the genus expansion of string theory at all orders. Yes. Yes.
So you're writing that as the ENs are for e to the
yes.
minus.
Yes. So remember that OX I wanted to interpret as e to the energy, and now the inverse of this I'm going to interpret as e to the minus energy. So I want to my Hamiltonian will be defined by this equation. Now the Hamiltonians that appear here are highly non-trivial. I mean, they look like Hamiltonians of relativistic fermions in a trapped one-dimensional gas, but they have very complete corrections to that leading behavior. But essentially, this is a Hamiltonian which is describing a particle with an kinetic energy which goes like modulus of p in a potential which asymptotically goes like modulus of x. Okay, so this is like a trap. We are going to study a trap Fermi gas. So I'm going to consider now a canonical ensemble of n non-interacting fermions, and the one particle density matrix of the system will be given by this inverse of this operator here. Now, once you consider this set of fermions with this peculiar one-particle Hamiltonian, you can study the canonical partition function. And there is a kind of a standard formula which tells you that the canonical partition function for such a system of n fermions is given by the determinant of this matrix, which is the density matrix, an n-dimensional determinant, and you have to integrate over these m variables, okay, with a 1 over n factorial. Now, this is a perfectly well-defined quantity for any Planck constant and for any positive integer. And for us, this was very important because we wanted to find a non-perturbative definition of a topological string theory. You want to have a non-perturbative definition, you better have something which is well-defined, you know, from first principles. And the fact that this operator is trace class and has this nice spectrum and so on, means that this quantity is manifestly well-defined. So this can be calculated, sometimes analytically, sometimes numerically, but it's manifestly well-defined. Okay, so now let me state our conjecture. Let's consider the following Toff-like limit for this canonical partition function. We take the number of fermions to infinity, so we are in the thermodynamic limit. We take h-bar coupling to infinity, so we are in a strong coupling regime of this gas. And we take n over h bar fixed equal to lambda. So this is a strongly coupled quantum mechanical problem. Now what we claim is that this strongly coupled quantum mechanical problem in the 1 over n expansion is equivalent to the weakly coupled topological string, in such a way that the log of this canonical partition function, which is the canonical free energy, has an asymptotic expansion in powers of 1 over h bar square, and the coefficient of each of this power of h bar square is h bar minus square is fg of lambda. Okay? And this is a statement which is valid to all orders in 1 over n. So this is the full 1 over n expansion. We are not just talking about the leading large n expansion. So if this conjecture is true, it's realizing the genus expansion of topological string theory as the Toft expansion of a manifestly well-defined quantity. And let me notice here that this is slightly different from what people did, for example, in C=1 string. Because in C=1 string, your basic model was matrix quantum mechanics. And then you were taking a scale, you were taking a large n limit, which put the Fermi gas in a sort of WKB regime. H bar was going to 0. Here we are in the opposite regime in which h bar goes to infinity. But what saves the day, what makes the problem tractable, is the peculiar quantum mechanics of exponential operators. And this was not long ago by Faddeev, that if you have quantum mechanics of exponentials of Heisenberg operators, there is sort of hidden S-duality in h bar, in such a way that the regime in which h bar is very large is also tractable. It's not only the h bar going to 0 regime which is tractable, but also the very large h bar regime. So this quantum mechanical problem is actually analyzable. You can actually make progress on it analytically, and this is very peculiar to this quantum mechanics of exponential operators.
Does your classical Hamiltonian stay fixed as you take h bar to infinity?
Yes. This is completely.
So naively, you would think that 0 point energy would go to infinity in this limit. You had a harmonic oscillator with a fixed classical potential. H bar went to infinity. Seems to set the gap off to it.
Yes.
Something like that happen here?
I think I haven't thought very much about the scaling of the ground state energy with h bar, because you know, this is a null order h bar expansion, so we actually take h bar finite and, large but finite, so.
But even in the harmonic oscillator, even between two states would
yes.
go to infinity.
Yes. But this is not a problem when you have to analyze the quantum mechanical system. As I said, there is this sort of S-duality structure which allows you to map this problem to a weakly coupled problem in a sense.
Are you measuring energy in units of h bar? Or are you measuring fixed energy as h bar goes to?
No, the energy is going to be a function of h bar, right? So the energy is not fixed. What I'm fixing is this peculiar quotient n over h bar.
Yeah, but when you compute your partition function, are you weighting it with Hamiltonian or Hamiltonian by h bar? Or?
No, I'm just using this thing here. This is my. So I'm putting beta to 1 if you want. The temperature is fixed, but h is fixed. Okay. Yes.
I have a related question, I think. So in case of C equal to 1, the e going to infinity and a bar 0 within that a bar equal to 6 was needed.
Yes.
In order to keep the total area of the Fermi drop.
Yes. Yes. Yes.
So you need to have a good larger unit.
Yes. Yes. Yes.
So in your case, how does it work? I mean, right? Because
Yeah, exactly. You could think, I mean, how do I know that this limit is in general will not exist for a quantum mechanic? When if you take an arbitrary quantum mechanical system, this limit does not exist or does not have an easy description. Again, the fact that this limit works well is based on this very peculiar property of this quantum mechanical system. So actually, you can see that this quantity here have a good soft limit in this regime. But this is not guaranteed. This is not guaranteed by the standard quantum mechanical arguments. Quantum mechanical arguments tell you that what is a good limit is n goes to infinity, h bar goes to 0, such that n times h bar is fixed. This is the standard WKB limit. This is a different limit.
And that's the same thing that was also done for quantization of Euler geometry.
The quantization of?
This Lunin-Maldersen geometries.
Well, I don't know if they were doing the same kind of scaling. Yeah. That I don't know. I don't think so. No, because they probably are in the weak coupling limit. This is really very peculiar to this system. So this conjecture turns out to have passed a lot of non-trivial tests in the last 2 years. And one very nice way of testing this conjecture is actually realizing that this expression is a matrix integral in disguise. This is actually taken out of the paper by Fredholm on Fredholm theory. So this is something that goes back to 1903. And this, when you write it down in detail, you actually can see that this is really a matrix model. And you can see that precisely this limit here is the standard scaling limit of a large n scaling limit of a matrix model. So you don't have to do anything special. At the end of the day, you will be able to use your standard large n techniques in matrix model to actually deal with this limit. Actually, in a sense, this limit is much more Toft-like, like the opposite WKB limit. Now, I have to say that mathematically, this is highly non-trivial because, on one hand, you have a non-trivial quantum mechanical problem, and on the other hand, you have all this string theory, which is computing all these Gromov-Witten invariants, so this involves algebraic geometry, combinatorics, and so on. But in spirit, it's very similar to SQL1 string and to ADS-CFT, and actually, in some examples of particular geometries, this partition function, this canonical partition function, is the partition function of a three-dimensional superconformal field theory in a three-manifold. In particular, ABAM on S3 can be recovered as one particular example of this construction. And in this case, this free energy of the topological string is the free energy of a physical superstring theory dual to this 3D superconformal field theory. So part of the ADS-CFT correspondence in 3 dimensions is recovered as a subset of this more general conjecture. Okay, so a sort of physical realization in some examples. Now you have a very nice situation because you have a 1/n expansion and you have an exact quantity. And when I was reading the paper by Spenta 10 years ago, I was actually working on the Gross-Witten-Badia model. Spenta actually did something very clever that at that point people were not actually doing very systematically, which was the following. Now, for the Gross-Witten-Badia model, there was the exact expression for the partition function in terms of this determinant, and then there was the large n expansion. And what Spenta was asking is the large n limit relevant? I mean, how close, to what extent, and in which domains of coupling is a thermodynamic computation in which n goes to infinity relevant for the case of finite n? And the question can be rephrased in many different ways, but in our case, the question is the following. Now, can we reconstruct this type of question, if we put it in our example, would be the following. Can we reconstruct the canonical free energy of the Fermi gas from its 1/n expansion? And this is a typical question that happens very often in physics. You have a perturbative expansion of some type, in this case it's the 1/n expansion. In what sense you can recover the exact quantity? Now, for this, there is the standard answer in the literature is the following. If the series is Borel summable, yes, you can. If the series is not Borel summable, no, you can't. Okay? Now, I'm going to actually give you a counterexample to this folklore statement. Now, it turns out that in many examples, the genus expansion of these topological strings is factorially divergent but Borel summable. Now we have, for example, plot here the Borel plane for a calculation involving the first 100th terms on this genus expansion of the topological string. And you see that the real line has no singularity. The singularities appear in the complex plane, but on the real line you have no singularities. In particular, you have no singularities in the positive real line. This is for a peculiar value of the modulus for this particular geometry. Now, this is fantastic. No obstructions to Borel summability. Let me do the Borel sum, and let me, this should be this would be the non-perturbative answer. But actually, it's not. In quantum mechanics, this is typically the case. Now it's going to prevent me, but just 1 minute more. In quantum mechanics, this is typically the case. For example, you take the quartic oscillator in quantum mechanics, the perturbative series is Borel summable, and if you do the Borel resummation, you recover the energy levels. Now, in the case of topological strings, the Borel resummation of the perturbative series is different from the exact answer. This is just something that you just can't compute. And they only agree to up to exponentially small effects. Now, the reason of this mismatch is the presence of complex instances, and this is not sufficiently appreciated. When you have a complex instance in your theory, you can have a Borel summable perturbative theory and still have a difference between the Borel resummation and the exact answer. And these are these poles here, these poles in these singularities in the Borel plane. This singularity in particular corresponds to a complex instance of the theory, which does not obstruct Borel summability, but has a positive real part, and there is an exponential small effect which goes like exponential of minus the real part of this singularity, which actually corrects the Borel resummation of the perturbative series in order to reconstruct the exact answer. So it's not true that Borel summability is enough. You have to be very careful with complex instances.
This means that there are two different non-perturbative answers that have the same expansion.
Exactly, absolutely. You can do the Borel resummation, or you can do the Borel resummation plus exponentially small complex instances. And this is very unusual. Very unusual. I think, in fact, I don't know any other example in quantum mechanics where you have exactly this. There are situations which are very close, but not exactly this. Okay, let me conclude. Now, models of strings based on non-interacting fermions were until now restricted to more or less low-dimensional targets. So we have these sort of models for 2D Mills or for sigma-1. Now, our construction extends this to the very rich and infinite family of non-compact Calabi-Yaus. Now, I have to say that, although I didn't mention it here, is that when you have these sorts of dualities, you can use them in both ways. Here I use this fermion construction to give a meaning to the non-perturbative topological string, but actually you can go in reverse. You can use topological strings, and in particular the invariants that Gopakumar and Baffa introduced, in order to write exact quantization conditions for these operators. And this is quite unique. You have these complicated operators, you can actually find their spectrum exactly, and you can find many of its spectral properties exactly using topological string theory. In particular, you can use this construction to solve the integrable systems that Goncharov and Kenyon introduced associated to the historical Calabi-Yaus. So we have now a non-perturbative definition of topological string theory in non-compact Calabi-Yaus, and this really gives you a model in which you really can sum up the genus expansion. You just use this Fermi gas, and this sums up the genus expansion for you. So we are still, I think, one interesting direction in the future is to explore quantum geometry using this very concrete model. There are many things that you can do. You can, for example, compute entanglement entropy for trapped gases. This is something that has been done a lot recently, and this would be, in this case, this would be telling you something about non-trivial holographic descriptions in topological strings and so on and so forth. Thank you very much.
You have these two quantities. One was the partition function of Fermi gas.
Yes.
Partition function of topological string.
Yes.
But I noticed you put a squiggle rather than.
Yes. That's precisely because
Equal or just,
this is asymptotic expansion. This means that this is an asymptotic expansion.
yeah, but is F equal to the Fermi
No, let me put it this way. This is a well-defined quantity, and this is a asymptotic expansion of this. You cannot put an equal there because these are different objects. This is a well-defined function, and this is a divergent series. This is completely well-defined. This is a number. For n positive integer and h bar positive, this is a number that you can compute.
Topological string partition function also well-defined quantity.
No, because it's defined by a genus expansion. It's defined by a divergent series.
Is it defined as a quantum theory?
No, you have superstring field theory of the topological string. Is defined as, the string theory is defined by a asymptotic expansion. So that's one of the big problems, right? So,
in principle, there can be more than one non-perturbative
Absolutely.
completions. So what can you tell about the freedom, in fact, to have such non-perturbative completions, let's say in this class of...
Yeah, that's a very good question. One way to do this is the following. You could say, okay, the most general non-perturbative answer, if you believe that the non-perturbative answers can be decoded semi-classically, the most general answer would be the Borel resummation of the perturbative series plus the Borel resummation of instanton corrections. And these instanton corrections come with unknown coefficients. So two different non-perturbative completions can only differ in exponentially small effects. So you could parameterize all possible non-perturbative completions by one single or a family of parameters which determine the weight of these complex instantons that can contribute. Actually, this figure on the Borel plane is very interesting because the singularities here tell you more or less what are the possible instantons that could correct the theory. And you see that there are various families of singularities that you can analyze analytically. And by putting some sort of arbitrary weight to all of them, you could consider what is called a trans series in resurgence theory, and this would be the most general answer. This is just a parameterization of many possible non-perturbative completions, but of course it's not very clever in the sense that it doesn't tell you, you wouldn't be able to discover ADS CFT in this way, I would say, or this duality in this way. At this point, I don't know any kind of constraint on the non-perturbative completion of this type of string series. I don't know. Even in standard physical superstrings, I mean, we know that ADS CFT gives you a non-perturbative completion of some genus expansion of type 2B superstring or type 2A superstrings in some particular backgrounds, and we believe that this is a non-perturbative completion, but we don't know if there are any others, right? I mean, there could be others. So I don't.
But there are Gaussian rules. I mean,
Yes, absolutely. You can think, there is the derivation or so.
There may be more than one answer.
Absolutely, absolutely. Here I'm not sure we have such a kind of first principle derivation. Yeah. But it was so hard already to find this one that But I'm not claiming that uniqueness is a property of this non-perturbative completion.
No, but this one was hard. But just Borel resumming was not.
No, Borel resumming is not, but Borel resumming is very trivial in the sense that it's a trivial. Yeah. No, but absolutely. I completely agree with you. I mean, we have two, Borel resummation and this other one. Yeah.
So I have a comment actually that if I take a theory of non-relativistic fermions with some single particle Hamiltonian, it is a very good example of non-commutative quantum field theory, which is constructed on the coadjoint orbit of W infinity algebra.
Yes.
And that is clear that it is true, but wonder whether there's any implication of this type of idea here in your...
Yeah, these are the papers you wrote with Avinash and on the coadjoint. Yeah. So I haven't still put these two things together, and one of the reasons is because the Hamiltonians appearing here are very peculiar. Have infinite number of corrections and so on. So they are. I don't know how easy it is to apply these techniques to these more kind of exotic Hamiltonians, right? Because these Hamiltonians are just standard Hamiltonians at leading order, but then they have infinite number of H-bar corrections. So.
I mean, conceptually, actually,
yes.
It throws some light on some new way of looking at this topological structure.
Yes. I mean, once you have this free fermion realization, I guess you can apply many of these ideas and try to get some new insights.
These Hamiltonians are quantum integrable.
Well, there is a more complex story. For this example that I was considering, there is a quantum integral system which is just one single Hamiltonian. Now, you look at more general Calabi-Yaus, then there can have many commuting Hamiltonians which are non-trivial, and then this sort of approach gives some light on these quantum integrable systems.
I was trying to relate that to because the W infinity is sort of a reflection of the integrability of the number of.
Yeah. I mean, for example, relativistic Toda is one of the systems that you can realize in this way.
Any other question or comment? Otherwise, let's thank Professor Marino.